Before we begin, a disclaimer. This episode was filmed in August of 2022, but the release was delayed by a year. From next week, we will be posting episodes closer to when they were recorded. Hello and welcome to Glitch, Bristol University's Computer Science Society's podcast. I'm your host, Salman, and today I'm lucky enough to be joined by Dr. Tilo Burghardt, Senior Lecturer at Computer Science Program Director. Tilo's main research areas are in computer vision and artificial intelligence, which we'll delve deeper into in this episode. CSS is proudly sponsored by Bloomberg, CACI, Publicis Sapient, Qualcomm, QRT, and Exmos. To see their latest job and internship opportunities, visit our jobs board at cssbristol.co.uk/jobs. Well, Tilo, it's an honour to have you as our first guest on the show. To get things started, I hear that you've just changed positions. What's your new role in the department?
Okay, I have just started as program director in the Department of Computer Science, and I'm looking particularly at our undergraduate curriculum for CS students. That is our MEng course for 4 years, our BSc course for 3 years, and also the option of an MSci that also runs 4 years.
Brilliant. I suppose some congratulations are in order. And with that, we can segue into my first real question. What got you into computer science to begin with? What was your journey from an undergrad student in Germany to where you are now?
Okay, this is an interesting question. It's quite a long and winded road that kind of got me here. I was always interested in computing, and I started to have a computer very early on when I was 11 and just tinkering with it and writing some tiny computer games. It was a Commodore 64. It's somewhere in the gamers' minds, possibly as a quirk of the 90s. But so from there on, I basically got into it by just trying anything you could do with a computer over the period up to my studies. And I studied media computer science in Dresden, in Germany. And I think the driver for that was the realization that was the late 90s, mid-late 90s when I started studying, 99 actually, in Dresden. And it was the realization that, well, civilization just takes a leap by connecting the whole world together. And it became clear at that point, mobile phones became smartphones during that time. The internet really started up to link not only, a few people, but, major parts of the world's population. And once you can communicate globally, for example, via media, and that's still, I think, one of the key things, how we communicate by images, sounds, ways that we perceive with our senses, that would usher in a change in how people live on this planet. And so I was interested in that. And I was also always interested in the natural sciences and nature generally. And that was another drive, and at least in my eyes, computer science is a fundamental science that sits, for example, in Germany with the natural sciences along mathematics and physics. It's called Informatik there, and it's rarely part of the engineering side of things as it is here in the United Kingdom. So from that point of view, it was this kind of interest of how the world is changing because of computer science and my general interest in the fundamental workings of nature and computer science being one of the core parts. I would call it running mathematics, right? It's mathematics underpins all of the natural sciences, but the difference that computer science has compared to pure mathematics is we got to compute, right? A mathematician can do an existence proof. Oh, there is a solution. If you're a computer scientist, you better produce something that is an output of a program. So there's a practical component to it, and that obviously links engineering and the fact that you build systems that work for the real world. So that drove me into computing. And then very soon I became interested in particular in the area of computer vision, which is basically an attempt to try to make machines see, understand what is happening in visual content, from images to videos to higher dimensional spaces that you could also take visual data in. And I looked around the world where there are places, and I was always interested in nature and applying it to the natural domain. And Bristol is really on the map because, for instance, we have the BBC Natural History Unit here in Bristol. And this is only one light tower project out of many who generate, collect, curate material of and on and about the natural world. And about a quarter to a third of all wildlife documentaries in the world touch down in Bristol at some point in their life. So it was a very interesting place. It's a very kind of central place to the IT industry as well. London obviously is bigger, but apart from that, Bristol is really on the map and has a nice kind of link to the industry and infrastructure also around here. And then finally, I was also attracted to the computer vision group here in Bristol at the time, which was headed by Barry Thomas. He was a professor here during the time when I started in 2002. That was, and he was a very, very inspirational person to me, and really kind of opened my eyes to the creative side of what computer science can do. And he had a background in NASA and helped program some landers, etc. So he was inspiring from his CV, but also inspiring as a person. And really kind of, I remember that my time with him, which led to the start of my PhD here, was so inspirational to see that actually our discipline is at the brink of creating something new, really new, on such a broad front. And his thinking was always amazing. I mean, he looked, for example, at interpreting videos very early on in order to help people who are blind, right? Just to interpret the world and transform the information you have in visuals into something that, a blind person can perceive, sound, for instance. So, I mean, it's loads and loads of things that inspired me. Unfortunately, he died in the first year of my PhD. It was a tragedy for the department, I think, obviously a personal tragedy as well. And then Neil Campbell, another reader here in the department, became my supervisor. And I started to look into applying computer vision to wildlife and understanding from imagery key things about wildlife. What species do we have in front of the camera? What individual do we have in front of the camera? What are the behaviors that these animals show in front of the camera? And these are fundamental questions that biologists usually ask in order to perform things like conservation, species analysis, behavioral analysis, understanding of populations and their dynamics. And traditionally, that was done with pencil and paper, sitting there with a binocular and, extracting how many individuals are there, what species is there, how long are they there, what behaviors are shown. And we started to automate that. So my very first projects were focused on African penguins, and I stayed for quite some time in Africa and actually filmed the species and built the systems to basically show that this can be automated. And it was some of the very early proof of concept systems that this type of thing may well be possible. And today, we have arrived at the situation where it's a central part of biologists' daily work. Camera traps have become a fundamental tool for capturing I would say, biodiversity wherever they're used. They capture behaviors, individuals, they capture the species, the movements of species, and therefore basically provide a lot of biologists with fundamental information about how the natural world is changing. And I think to summarize and to kind of end up on, the personal trajectory that I've taken that links actually what drives me now to my personal journey is, I think we've arrived at a point where a great problem that we're facing as a planet, which is shrinking biodiversity and us as a species taking over so much of this planet, that the natural systems are, coming under so much pressure that we're not quite sure where this is going to lead. And on the other, this is a fundamentally big question. Can we even survive as a species once we suppress the natural balance and environment of the planet so much that it may not on its own function kind of as evolved. And then secondly, we have this great opportunity in a way, which is artificial intelligence and the rise of computers that can actually aid our activity. And bringing these two things together is really where I see, the role of our community and my personal role of trying to use AI for good in order to first understand what, the planet changes are all about, and then intervene and try to use the information we've gained in order to do conservation, do better animal welfare in farms, for example, anywhere where humans and animals naturally interfere. And that drives my research today. That is my passion in the field. We were some of the first who started trying that. And I think the field is now maturing to a level where the world community is starting to take notice. And even big companies like Microsoft and Facebook, etc., start to draw some attention into these areas and put resource there, which has not been the case for decades.
It sounds like your initial interest in media computing was piqued by more the HCI side of computer science. What led to the shift towards computer vision?
The two things are actually quite linked. If you think about it, we are the perfect computer vision machines. We open our eyes and the world unfolds in front of us. We're interpreting naturally the environment around us. So thus, the media we perceive when we, open a Facebook page or, browsing YouTube or whatever we do, at that moment, we are doing computer vision. We are doing this. And it is just our ability to do that seems to generate our very efficient way of interacting, not only with the natural world, but also with the media world. So the step really from studying media, studying how you, put a video on a DVD, that's one of the things we've learned first in that course, etc. And how to actually interpret the semantics of it, the meaning of it, is not that far removed. Actually, they're intricately linked. It is often that from the low-level features that are stored or saved, etc., they're the fundamental building blocks of extracting high-level information that in the end describes what's going on in this clip or etc. So for me, that step was small. And in fact, there are even areas like the My World project, which tries to really link in media creation and AI together in order to create more, is proof of that it's, this dimension is as active as today, and as it has ever been. And take the example, for example, of compression, right? If you want to compress a signal, the more information about the semantics of it you have, the better, right? If you know how, for example, a human face is structured, etc., you can compress videos of interviews, etc., much, much better, because you can replace all the information you already know, in the video. You can take that out and only transmit the information that is differing from video to video. So high-level semantic information is actually directly linked to the media that carries it. So the step is small, I would say. What role the human plays in all of this? This is a big question that is, I think, generally a big question in machine learning and AI at the moment. And we have the interactive AI that is led by Peter Flach here at the department, where doctoral students try to explore that space between the machine learning side and the intervention of a human expert, and how the two can actually play together in order to create better systems, better understanding, etc. And this is still not fully exploited, understood, how our abilities, intellectual abilities, and the ones of machines can be brought together in a system that is really optimizing for both parts, the human expert and the machine learning algorithms and the exploitation on that side.
Okay, and you've had quite a long career in this area, so how much has the landscape changed since you first started?
Massively. Absolutely massively. When we started off in the 90s, people used geometric algorithms in order to understand videos, trying to fit ellipses and fit basic shapes in order to find things. And And then major changes happened in the early 2000s. Stronger AI systems emerged, like whatever random forests and SVMs were coming out at that time. So it gave a boost towards learning systems. And then, as you know, the deep learning revolution happened in the mid 2000s with large annotated data sets and the ability of producing quite deep networks and then apply backpropagation using GPU power in order to actually overcome some of the problems that had hampered neural networks for the last 40 years before that. So I think that's made a big step change in terms of particularly visual AI, but AI in general. And I think the field has completely changed. And if you studied it in the early 2000s, if you studied it now, there would be very little overlap. I mean, there's overlap, of course, but in biology, the fundamental rules won't really change. Whilst in this field, the fundamental rules have changed. And, what we're teaching, for example, in applied deep learning here as now the standard approach to deep learning would not have been taught at all as any sort of standard approach in the early 2000s and wouldn't, have been known by then at all. So a lot has changed. And as a result, the quality and breadth of applications that computer vision brings out has changed as well.
You mentioned how artificial intelligence has changed, and I feel like artificial intelligence is quite a loaded term now, with it often being used interchangeably with machine learning. What does artificial intelligence mean to you? Did your work start as machine learning?
Okay, this is still a very debated topic, I would say. What is intelligence? Let's start with that. And the biologist possibly would tell you it has something to do with the ability to adapt to change. And clearly, the type of networks that we're training today have very little of that ability to adapt to true change of the environment, i.e., operate on completely unseen, ununderstood environmental inputs. So from that point of view, you may argue, well, it's actually not artificial intelligence. It's rather truly some sort of learning using a machine. So the term machine learning would sit much closer and better there, I would say. On the other hand, in terms of capabilities and the fact that for very specific tasks, AI systems can well outperform humans, you could argue that that is some sort of specialized form of intelligent behavior. And therefore, it's still a discussion that is roaming, leaving the sentient and conscious related side completely out of the discussion. Okay, but point I want to make is what has changed is the quality of prediction that these systems can make. That has changed dramatically. Even for the very, very first systems, you had jumps in accuracy that were well over 10%, just out of nothing, out of nowhere. That's what deep systems allowed you to do, classifying images in terms of what's in them, suddenly much better. And I think if you want me to summarize kind of where the key lies in large amounts of data can now be utilized with these systems, whilst older machine learning or machine vision systems were often limited in terms of how much they could utilize or how well they could utilize large amounts of data. So we're still at the age where it's gold dust to have large annotated data sets, although things are moving now towards self-learning systems that utilize self-supervision signals in order to try to avoid human input. And that's the point where the field is now trying to minimize actually that teacher behavior that kind of was the core of how we built these systems, by providing pairs of some input and then the desired output of some sort. But when you move from this world where a human looks at images or listens to sounds, etc., and then produces a class for that, and then feed the machine with this pair of input-output, which still most systems take as the core, towards a world where the system tries to find groupings and clusters and areas that fit naturally together in order to learn, based on all sorts of signals that may be dominant for the domain or important for the domain, then you see there's a shift, right? And this could be simple things like what was done in AlphaGo, where systems play against each other in order to improve based on simulated outputs. up to the idea that you trial and error in the real world, where robots actually learn to walk by walking, really. And this is a step change. And at the very beginning, it was very static, and now this area starts to move into a more dynamic, interactive pathway. And if you think about how we learn, when we were children, how we learn from the world around us, then we also interact, and we learn by interaction. Nobody has walked without ever falling before, and it's important because once you fall, you know how not to walk, and that leads you slightly in the right direction. And that type of stepwise reinforcement by more and more exposure into the environment is a fundamental kind of driver that is more and more taken into account with respect to building machine learning systems. And now you can judge for yourself what that means, whether machines really become more intelligent in that way, or whether it is still one dull learning task if I give you an environment and you adjust and adapt to perform well in it.
Do you think that in this time the relationship between industry and academia has changed? In particular, where the most cutting-edge developments in AI are happening, and how university works with the industry now?
I don't think I can fully judge it because I've never worked a long time in industry. I mean, as an employee of a major company. So I don't think I'm quite in the right position. You should ask someone who has had that experience. But by working with industry, which I do have experience, I would say that it has become a much more even game. And there's strengths that universities have, and there's strengths that research departments in large companies like whatever, Google, Facebook, Uber, you name them, have. But and there's some complementarity and some overlap. I think universities still have some sort of the luxury of starting to think about topics which may be of no immediate, commercial or wide-scale use. And that's, that is a luxury. That's also quite pleasurable to start just intellectually approaching some of the topics that come up there. On the other hand, the resources that large companies have started to completely outweigh what universities can muster. And therefore, there is clearly, something that is difficult to replicate now for even university consortia. But some governments started to respond by building large computing clusters that can be shared by universities, etc. So there's directions that governments and nations and consortia take in order to approach that and say that also the let's say public infrastructure kind of starts to not match up, but go in the direction of what these large multinational companies have in terms of computing power, because that is unfortunately in AI a fundamental metric that tells you how far you can go in terms of trying things out. And it's an important measure. It's not the most important one, I would say, but it's an important measure to have that computing capability. And I always find it also important that staff and also students have access to that here in the university, right? So that's fundamental, right?
You've touched on an interesting topic, which reminds me of a post that got quite controversial on the ML subreddit a while ago, where many users felt that the papers published by these big tech companies got a lot of media attention, but didn't actually solve anything new, and rather they took problems that had already been solved and just threw the sort of compute at it which only they have access to. Do you agree with that assessment of the situation, or share those frustrations?
Well, I mean, there is an issue. For example, reproducibility is some sort of an issue. If you have a cluster that no one else has in terms of scale, then, by definition, no one else can just try the same thing out and come up with similar results or something like that. That is one issue, is reproducibility, but it also skews the field slightly, because if you have masses of data, masses of compute power, you gain a natural advantage in terms of, potential accuracy of your systems. And if you measure papers by the quality measure of accuracy alone, say, then yes, it's highly likely that the biggies will outperform some of the kind of smaller players in the field. But this depends really how journals and conferences and publishers in general approach this and review this, because, really the intellectual advantage that a paper sells and produces and shares with others, because that's what a paper really is about, of sharing knowledge with the community. That's why you publish a paper. You share it so that others can utilize it, understand it, and scrutinize it. And I think there is some limits on that if you just play on big computing facilities. But it's the judgment of the reviewers and the editors who should value ideas beyond pure accuracy values. And that's a challenge. That's a challenge. I mean, I'm sure that you find good and bad practice in this field out there. So I'm not sure I agree fully with that statement, but I can share some of that frustration, and it's natural. But I mean, in any field that will exist, right? I mean, if you go in any field where you have a major monopoly or major player, it will be difficult for smaller players to, enter that market or, compete. But as I said, I think the key should sit with editors and reviewers who should look at ideas. But then again, it's quite tough to judge ideas in terms of quality. And it's quite easy to judge accuracy in terms of their ranking. So that is a temptation, I guess, that people need to resist.
I guess on the other side of journals is about science communication and how these discoveries are communicated to the general public. A lot of the big buzz in general media recently has been about generative AI, things like Imagen and DALL-E or GPT-3, which have come from bigger companies like Google or OpenAI. Do you think that more work needs to be done by universities on that science communication front to make sure that general public is aware of the research that's happening?
Well, I'm not so sure. I mean, science communication is important, it's central, but really the task of a university is to do research, not to produce a product. So universities have a duty to connect with the public and do outreach and share information, publish information, and contribute to society in that way. But they don't have any commercialization kind of duty. Of course, it's nice, and they should facilitate it. And, you should have, put people on track to start their own companies and team up with companies. But I think there is science communication absolutely fundamental. And universities should take the lead in it. Yet, I don't think I would have a big issue of companies, going out there and trying to, in my case, for example, to take Microsoft AI for Earth, right? A big, I think, $50 million investment a while ago. And it was an initiative in order to try to bring both to the public as well as to the stakeholders in the field capabilities that Microsoft would produce in order to help wildlife farming around the world. And that must be a good thing. I don't think it should only be in the hands of universities. So I have no big issue with companies in general trying to do the right thing, if that is what the science communication does.
Out of curiosity, does the public perception of these things affect how easy it is for you to win funding for your research projects?
Maybe. I don't know. I come from a German system originally, and in Germany, it's all different. I mean, there's a different fee system for studying. I mean, it's much lower, and it is that research institution like the Max Planck Institutes or the Fraunhofer Institutes, etc., are even partly separated from university sides. I mean, universities do research, but then there exist these kind of national research institutes, if you want. So from that point of view, there are different models around the globe that all try to, basically fill the landscape of research and teaching and education and science communication with entities that do it. And I don't think I have a major preference there. And I think different universities have different strengths in different parts of that. But I think the core role of any university should be research, teaching of the next generation, and engaging with the public and industry in order to turn their ideas that they have into input into that industry. And I think, around that, every university will find their own space that, fits the local place where the university sits, fits the demographics, fits the industry landscape, and also fits possibly the scale and ambition that people can muster in that. So Yeah, I'm not so sure I can give you one answer here, and I think there are different models, and each can work right in their own way.
It would be remiss of me to have a podcast episode about AI and not talk about ethics. So, what's your ethical stance on the risks posed by artificial intelligence as it relates to your own work?
I personally have a very strong view about the ethics side of applying vision systems or AI in general. And whilst I've worked on health projects, human health projects, etc. in the past, for me, since the realm is, I think, not sufficiently regulated at the moment, I removed myself from any new projects that work on humans because I think some sort of control in this domain is really needed in order to, well, pay tribute, I would say, for the enormous potential and also potential to do damage that exists now in these capable systems that in some areas perform well beyond humans.
Is part of the problem that universities produce well intentioned research, but profit driven companies are the ones who eventually productize and monetize that research? Would academics not have more control over preventing misuse if they were more heavily involved in the productization stage?
Yeah, but how far do you want to go there? I mean, the responsibility lies with everyone along the chain, right? From the person who has the idea on a whiteboard to the person who commercializes it and brings out a product that, pays. I don't think you can just, compartmentalize that. Every stage of research has an ethics component to it. And you always need to be aware of where will this lead, what role do I play in this, etc. For me personally, mathematics and ideas as such, you can't suppress them. They're just factually out there. But in the moment you apply an idea to data, and particularly in AI or machine learning, in that moment you're producing working systems, working products. And at that moment, that's where real scrutiny needs to be applied. And that is usually the moment you train a system on particular data to do a very, very particular task. What you utilize it for is then even further down the line, right? Do you use your face recognition system in order to control entrance to a particular building, or do you use it in order to find someone in a crowd, or do you use it in order to, do worse things with it, right? So that's, but I think every stage after the ideation stage needs to take care of that. And even at the ideation stage, in the moment when you conceptualize an idea, you need to kind of foresee a little bit of what path that may take. And it's tough. And I don't think bringing universities naturally very close to industry will solve this problem. I think everybody needs to be, well, at their best of their game in order to, have the whole pipeline of development covered by an ethical code. I would like to see that to some degree regulated.
What sort of regulation do you want to see implemented?
It's a very, very good idea. And I don't think I have the wisdom there to kind of tell you an immediate answer. It's a big discussion between many people. But I think just when it comes to human beings, GDPR is just the first step towards trying to limit the impact on privacy, the impact on my worry in general is that if you produce machines that understand human beings with respect to their behavior, their identity, their interactions, their roles as an individual, as a group, as a society, at that moment you have tools which have enormous power, enormous power. And to regulate, I think, would be to control the utilization of this power. That is the fundamental thing that I think needs to happen more than is happening right now. But that's a personal view. And on the other hand, I'm also, for complete freedom of ideas and free discussion, because all of academia is kind of highly dependent on the fact that you can discuss ideas openly, frankly, and clearly. So this is a very fine line. I don't have the answer to that. I just believe that some major resources need to be invested in this area from everyone from philosophy, politicians, people working in the economy, scientists, computer scientists, in order to together produce this. And I think we're just at the starting point of that, because really to see the societal implications of this, it's not even clear in many cases where it will lead. And there are big question marks over, what would happen if.
So your research is primarily focused around ecology and wildlife conservation, but I'm wondering if there are any applications of it outside of these areas?
The application field is very wide. In general, my research aims at utilizing machine learning in order to understand media of wildlife or animals, even under husbandry or captive situations. And the purpose of it is, as you say, efforts towards conservation. But really, if you think this area, I call it animal biometrics. Other people may have slightly different wording for it, but in essence, if you think this further, where will this lead? Where is the general direction? And I think fundamentally, it will allow people to start linking the phenotype, which is, the animal, its behavior, its way how its body and interacts in its environment, and the genetic side of things, the genotype, because these kind of, I would call them almost layers or different levels of abstraction in life, in living organisms. They really make up what we understand as life. And so far, bioinformatics and the genetic side of things has made major progress, big milestones being whatever, sequencing of genomes, understanding of genes now, first applications in the pharmaceuticals and, etc. But the phenotype area is only in the very early stages. And whilst people start to use cameras in order to help with, say, vertical farming and optimal plant growth, and kind of filming the leaves and understanding what changes in the environment will help the plant to grow better, etc. And we are trying, for example, a lot of things here in our farm to help welfare on cattle, where we identify individual Frisian cattle by their coat patterns, by their white and black areas, and then start to track them, etc. And that will help produce that level of information, of understanding from data that people started to do on the genetics side. So really, in long term, anywhere where the physical presence and measurement of an animal and the genetic side can be linked somehow, this is the long-term link, and that, I think, will be a major contribution towards a new direction of how the natural sciences understand life. Because that link is an information link, which is currently unknown. Some people would call that fundamental biology to understand that link, but I believe that the realization of that will have a component which has computer science really at the heart of it, because what you need to do is measure and interpret these measures and then correlate the interpretations of the measurements to the next layer of life, really up and down that kind of grand hierarchy from the DNA molecules up to the entire organism and its behavior. And I think this is a possibly 50, 100-year task, but we're starting off now by starting to interpret animals semantically, understanding meaning of behavior and species, and trying to build species spaces based on observation rather than DNA. Do they match? Are they the same? If you look at the phenotype and the genotype, can you see clearly similar phylogenetic trees or not? Do they differ? Right? Because, before genetics was active, people looked at animals and said, oh, they look similar, so therefore they may belong to a similar, say, family of animals, etc. And now genetics has taken over and say, okay, we can very, very clearly kind of build the relationships between life's branches based on DNA. But then to link back to the actual phenotype, to the actual organism, is still to some good degree an open question. And I think that is the big direction where this is leading. I think proper understanding, deep understanding of the phenotype of animals, of their behavior, of their physiology, their morphology, their being in general, right? And that includes humans to some degree. But obviously, that's the area where, I think there are bigger issues to address.
This is perhaps treading too deep into the territory of computational neuroscience, but if your research in animal biometrics could help in understanding animal physiology, Do you think that eventually this understanding could sort of feed back into how we understand AI and help us improve the models that we're using?
Goodness, you should ask Connor that question. I don't have any good answers on that front. Maybe. I think the real key question is, in how far can artificial intelligence or machine learning be getting closer and closer to intelligent systems generally. And by intelligent, I mean truly intelligent in the sense of being able to adjust to change generally. And if that is the case, then we're in a position where it is very difficult to differentiate between what we think is biologically intelligent life and machine-based intelligence. But I think we're still a little bit away from that. This is not around the corner, and I think there's a lot of questions to be addressed before some sort of true general intelligence can be shown by and even some recent thoughts that some language interpretation model also has properties that actually show intelligence. I would highly doubt that on the basis that the real kind of intelligent behavior is one that interacts between environment and the intelligence system, where the intelligence system adjusts to that environment and really changes itself in order to adjust. Whilst most of these models that are trained today don't have even that adjustment loop in them. They're just trained on massive amounts of data that they've been exposed to in the past and then react based on that past knowledge to a current situation. That is still in many areas the fundamental kind of driver behind it. And to really kind of move from that to a truly interactive system that adjusts to any change in the environment or input space, I think we're a bit away from that.
And so do you think that the idea of having artificial general intelligence is feasible, or is it sort of just a sci-fi pipe dream?
I do not know. And I think in science it's important to say when you don't know. I do not know. It's kind of the billion-dollar question, isn't it? Is it something that can be easily replicated? If you want me to have a guess, I would say the guess is yes. Why should a carbon-based biological system be the only one that captures properties that we call intelligent? I would wonder whether that statement, it doesn't quite ring true, does it? But then again, I do not know. I think that's as clear as I should say it. But that makes part of the excitement and passion for this area to start to really try and understand the next level deeper of what we're doing, and therefore being a little bit closer to answering exactly that question of what would it look like? I mean, as an engineer, we're always looking at things like, I understand something when I can build it. When I can build it, I understand it. That's the moment when I really understood it, when I can create it out of something. And that's slightly different to a scientific approach which describes it. It's a descriptive process, whilst engineering is a constructive process. If we have an intelligent system, we better be able to actually create one rather than talk about it and its properties on its own. So, okay, I think, I don't know, but my inkling is, yeah, I can't see why not. I can't see a killer reason why this wouldn't be. There are other people who have strong views that where we are currently is very, very different to what intelligence means. I mean, I don't know what you think about Roger Penrose, but he has a strong feeling that there's something different than traditional computation to what human intelligence is. But up to you to kind of choose your belief in that area.
What's holding us back right now? Like, what's the big problem that's holding back progress in AI that once solved will open the floodgates of progress?
Well, there's always the PNP problem. That always exists. And, if you crack that and come out with P equals NP, which, very few people believe, if the two spaces are really kind of mergeable, and there are algorithms that speed up computation of such difficult problems massively, that is still a game changer. It hasn't changed because of the deep learning revolution, I would say. But Otherwise, I think the field is diversified to a degree now where it's such a broad thing, apart from, general artificial intelligence, which, the holy grail of what people try to do, saying, if I learn how to learn, if I know that properly, then, all the specific problems just, you know, are not problems anymore because then I can learn them from based on one algorithm. Uh, I think the proof is in the pudding here, and I would wonder whether such a free lunch is easily achievable.
Your research sort of sits at that boundary between computer science and other disciplines, so I assume that you'd need to work quite closely with people from these other disciplines who might not necessarily be tech people and might not understand the lingo. What's that process like? How do you sort of effectively communicate what's happening in the cutting edge of AI research to people who may not necessarily understand the technical stuff?
I think you cut on something that, particularly for the area I work in, has always been one of the reasons why I still, after 20 years of being part of that field, I still really, really enjoy it and find it interesting, intellectually stimulating, and horizon widening, because people from so many different areas, biologists, people who work in the field, mathematicians, people who apply things in terms of the engineering world out there, writing apps for people, people who are experts in the biological domain and behavior experts, etc. I learned so much about areas that I didn't know anything about. And as a computer scientist, it's quite enriching, I think, because you see your own area of research, of application suddenly mirrored in the mirror of other disciplines. And you see different things. You kind of get a reflection that is actually revealing about what you're doing. And therefore, it's enriching your view on what you're doing. And that's what I find so fascinating about this, that after 20 years, it has not been exhausted whatsoever, and is possibly even more vibrant, this exchange. Do we speak the same language? Not quite, but that is the interesting bit. The fact to try to understand what our spaces of meaning, of understanding are, and how they correlate. What does it mean in your domain to do X? And whilst computer scientists often have a kind of procedurally accurate definition of how things work, I mean, that's really what a computer program is. Other disciplines have other approaches to it, and they have more a descriptive approach of things, accurately descriptive, or categorization-wise, kind of more clustering the field of possibilities in a different way. And I think I learned a lot about computer science by speaking to people who are not computer scientists, because it makes you think about our models, our approach, in ways that are unusual within a computer science only field. And I would say to anyone who studies computer science today, consider it really a hub discipline for a career. Whilst it's a science in its own right, it's an engineering discipline that has major reach into society, industry, and possibly even the philosophy of how we do things. But on top of that, it's a real hub, and it allows you to talk about information, and everybody is using information. Absolutely everybody. I haven't come across a field of human endeavor where information is not critical. And that's really what is fascinating about the area of what we study, what I'm passionate about, all my colleagues are passionate about here in computer science. And I hope that this is also one of the motivations that students who start here and want to understand and learn about the field and take up a career and make changes in the field, I think that is one of the drivers, is that it's such a hub. I would even say that many of the fundamental natural sciences in the end deal with information. And how you describe the physical world, how you describe the chemical world, the biological world, in the end, it's a system of information. And since it is that, we have tools in computer science, how we can deal with that, which sometimes differ to The scientist would deal with it. And that is where the fruitful exchange immediately starts and where the discussion becomes interesting.
Are there any opportunities for computer science students to get involved with this sort of interdisciplinary work while they're at university?
Well, I mean, the easiest areas are internships, where you go into industry in Bristol, say, during your studies and find out what companies do. I mean, companies engage computer science in the real world. That's the kind of easiest, lowest hanging fruit to really find out. And obviously start networking, learn how industry works. So that is one aspect. Another one is starting to have conversations about your final year project, etc., with members of staff early, and just get a little bit of exposure of that research area. That can also be maybe in a summer internship where you still learn something with a research group, etc., or just start an exchange with one of the academics in some area that you were taking up for your final year project, my potential supervisor, etc. So your final thesis is your opportunity to, grasp a topic and actually, get outside input into computer science as well. So it doesn't have to be a computer science only project. I think in most cases it has a real world link that goes out there, maybe not only to the sciences, but to the social sciences and to the city and, to the things that people do. And I think that creates that link as well. And then finally, I mean, we all live in the real world. So we have daily experience, always, about how computer science interacts with the world. You open your smartphone and there you are, right? You switch the telly on and there you are. You use an app to order some food and there you are. So you're exposed all the time. And just by starting to reflect, think a little bit deeper. How does it work? How should it work? How does my discipline that I'm studying right now actually map to things? This is how many entrepreneurial ideas are born. This is how many kind of fields of research are starting off by questioning the reality today. What is out there? What could be out there? Why is it not? What do I need to do in order to, change that little aspect, that tiny thing in the world? And I think that everybody can do that. And the deeper you go in studying computer science, that world is opening quite widely. And I should add that luckily we're a discipline where our world is quite open online and all the papers are available in most cases for free in computer science, because most of, at least in my field in computer vision, the top conferences and the top papers, they're all available for free for everyone to read. There's also a lot of lecturing material and course material beyond what you see here in your studies online. So you're really in a space where the information is there and you can kind of immerse yourself in it beyond it. And I recommend it to anyone because it's horizon widening.
Looking back on your career, are there any papers that you've published that you're particularly proud of? Either because of their societal impact or because they've had a big technological impact on the overall field?
Okay. I think I shouldn't make that judgment myself. Others should make that judgment. I think it is fundamental that whatever we publish is basically sharing our findings with the wider research community. What I think I'm very happy about, let's put it this way, is that recently we started to come together as a global community working on AI for wildlife, on AI for conservation, etc. And that is only a very recent development. And I'm very happy about this happening. And we published a paper this year in Nature Communications where we basically summarized the big challenges in this field in a global community. And we were all kind of small co-authors from all around the world coming together and putting this together as a kind of here we are today. And these are the main challenges we face. These are avenues where there are great solutions and a potential for great solutions available. And that's kind of a little bit of the next roadmap that we should take. And I think that type of communication amongst the group of researchers, I think that is the thing that is really needed. And it includes a biological view and a computer science view in my field. And then we've done, lots of small things. We built the first, autonomous drone that can identify individual animals. find them and then identify them and then move on to the next one whilst the animals are freely roaming. So yeah, it's small things, but these proofs of concepts are important because they show actually something is possible. And if you can have a drone that can find an animal and ID it as an individual, what can you do with it? Now people can start thinking, right? And turn that into their own application scenarios, and that may be conservation, that may be farming, that may be, any area where, where people have an interest in finding out and then applying it, hopefully, to the right areas. And I mean, in our case, it's mainly driven by welfare. Do you understand, all animals in a healthy place and not separated from the group, and all this type of thing. I mean, there's various things. I mean, which I think were important steps, but they're all small contributions to a bigger picture. And this is, I think, most of science works like that. It is rare that there's this one big breakthrough. I congratulate anyone, for having that. But the major kind of body of work of science is a continuous progression that's made up by small steps by many people. And I think, for me at least, science is that, extending knowledge in small but clear steps, share that with the world, with the community, and thereby progress what we are as a society, what we know in terms of our knowledge of the world, and maybe then drawing conclusions about implications of how the world of tomorrow should look like. So that's where science sits for me. And as I said, I congratulate anyone for great breakthroughs, and the story of science is often one of these great breakthroughs because that's what you see in the media. But I think the fundamental carpet of progress is really one of many people, many small steps, and moving the whole domain forward. And whilst you can pinpoint, say, in deep learning, various kind of seminal papers that have sparked new directions and new waves of progress, it is also the kind of diversification of the field now into all sorts of areas that impact on our society and everybody's life that really have made the field the success that it is today.
We are coming to the end of our time, so to wrap things up, let's have a round of quickfire questions. What's your favourite programming language?
Ooh, C.
Least favourite?
Oh, God. I have no idea. I would have to think very, very long about that because the list goes down quite some way.
Tabs or spaces?
Spaces, actually.
And lastly, do you have any programming pet peeves?
No.
And finally, where can people go to find out more about yourself and your research?
I mean, for any researcher, find their papers, read their papers. So you can go to my website, you can go to Google Scholar, look there. In general, read the papers, and they should be clear enough about what we've done and what the research has done. So that is usually the direction. Or talk to me, see me in the corridor and have a chat.
Well, that's all we have time for today, but thank you so much, Tilo, for being a guest on the podcast, and thank you for an interesting conversation.
Thank you, Simon. Thank you.